Good afternoon, participants. Sir, let me start the session, sir.
Okay, sir, sure.
Okay, sir. You can share your screen, sir.
Yes, sir. Is my screen visible, sir? Hello.
Yes, sir. Visible, sir.
Okay. Screen share also is working, right?
Yes, sir.
Okay. Okay, sir. Okay. Thank you. So, good afternoon, all participants. Hope you all had a great lunch. So, let us start from wherever we had left. So, we stopped here, right? We just had the theoretical backgrounder for an 8-bit SAR ADC design, and we were trying to design it and verify using discrete ICs before we move into circuit level design using any of the technology libraries. Okay, so for design using discrete ICs, we are planning to use an ORCAD PSpice tool, which has over 200 IC libraries that are included to the tool. Okay, and we'll get a fair bit of idea of what to expect out of successive approximation register based ADC. Okay, when we go for a system level design using any type of technology nodes, whatever is the technology node, at the end of it, it is going to be it is going to be an analog to digital converter. So the outputs are going to remain the same. Okay. It is about what is going to be at the logic 0 and what is going to be at the logic 1. That's what matters. So let us move forward without much delay. So um, we are about to start the design with an R to R ladder digital to analog converter, followed by that the successive approximation register using D flops, and then a comparator design. Along with that, a sample and hold circuit. Timing control and alone we are removing it since we are still in the process of designing. We have already completed it, but we are still facing some glitches. Once it is done, we'll be ready with the full circuit, and then we'll integrate all the blocks one by one, um, and check the output at each and every stage so that we make sure that everything falls in place. Okay, and then we'll go for functional simulation uh, for the overall circuit. Okay, now let us move forward. Let us start with the slight theoretical background on R2R digital to analog converter. So it is a digital to analog converter which uses two precision registers to convert a digital binary number into analog output. Okay, and it is going to be a ladder network. So what is a ladder network? We are going to use two resistor values, one with the base value R and the other one and is going to be twice the value of base resistor. Okay, and this is how the ladder network looks like. Okay, so what we have to do is we'll have to measure the equivalent resistance all the way. Okay, we have to measure the equivalent resistance, and then it will be looking similar to a Thevenin's equivalent circuit, where a resistor is connected in series with an voltage source. Okay, that is what is a Thevenin's equivalent circuit, right? So that is how it's going to look like. So how to do that? We have demonstrated it stage by stage. First, we are going to, so you see these two resistors are in parallel, right? And uh, get an equivalent resistance for this. Okay, and then This resistor is going to be in series, so we can apply voltage divider rule. So by that, this is R3, this is R1 and R2. Okay, so R3 plus this resistor is going to be in series with an equivalent resistance. Okay, so R3 plus R1 R2 divided by R1 plus R2. Okay, so we get the value of those resistances, so it gets it is similar, it is equal to 2R. uh, so this is totally about connecting the resistors in parallel and series combination. And if all the binary inputs are grounded, then the corresponding binary code is 0000. Okay, all the 4 bits are going to be 0 when all the inputs, these are the inputs. Okay, when all the inputs are grounded, then the overall binary code is going to be 0000. This is about a 4-bit ladder network, but we are talking about an 8-bit SAR ADC, right? So whatever circuit it is, okay, it has to be expandable. Okay, so we have to parameterize it, okay, or we call it as generalization. Only then, irrespective of the number of bits, we'll be able to expand it accordingly. Okay, so just give me a minute, I'll be back. uh, Sorry for waiting. Okay, sorry for making you wait. So we'll continue. This is about this is how we have to reduce the circuit, and finally we'll be arriving at this part. Okay, so by using this equation, we will be measuring the value of output voltage. This is what will happen to the entire circuit, entire or to our ladder network, and finally we'll get the output voltage value. Okay, so we have to minimize, or we have to get an equivalent resistance at each and every stage, and finally arrive at this kind of circuit. Okay, so in case if we, so this is for uh, this is when all the input voltages are connected to ground, that is going to be equal to 0. What happens if there is an output at any one of the stage, or 1 or 2 stages? Then how will we measure the output voltage? Okay, it is like this. So if we have the input voltage at has the most significant bit, okay, then what is going to be the output voltage? If we consider the Thevenin's equivalent circuit with the same combination, then the change in voltage will be 1/116th of the input voltage for a 4-bit. Okay, for an 8-bit, you have to imagine in that manner: 1 by 32, 1 by 32, 32 of the input voltage will be the difference. Similarly, if the input is going to be at the second bit, okay, then the change in voltage will be 1/8 of the input voltage. For the third bit as input, it is going to be 1/4 of the input voltage, and similarly, if it is the last bit, then it is going to be half that of the input voltage. Okay, so this is how we have to figure out the value of output voltage when it is in terms of an R2 to R DAC, digital to analog converter. So we have given you the value of output voltage depending on the inputs. Okay, if all the inputs are at active high, then your output voltage is going to be 4.6875. In case if your supply voltage is 5 volt, then your output voltage from the digital to analog converter is going to be at 4.6875. Okay, it's not going to be equal to 5 volt. Why is it not going to be equal to 5 volt? Any idea? So I'll leave that to you. Okay, try to figure it out. Okay, so this is going to be the generalized equation for an 8-bit. So for 4-bit, we have got the output voltage, value of output voltage. Similarly, if you are planning to expand it for an 8-bit R2R ladder DAC, then this is how you are going to measure the output voltage. Okay, and this equation is the generalized one for an n-bit uh, digital to analog converter. Okay, and this is how we have designed the blocks. uh, this is for an digital to analog converter, 8-bit to a DAC. We have made use of switches over here, and in order to avoid glitches at the input, we have included a buffer. And here we have the supply voltages. We are using an amplifier in order to measure the output voltage. And here we give inputs at different frequencies. So for an 8-bit, we are going to have 256 steps, right? So that is what we have here, and it is going to count down. Okay, 256 down to 0. Okay. Fine. So this is the circuit for an R2R DAC, and here you can see there is a mistake in this ladder network. The reason is it is not balanced. This is the ladder network that we have. It is not balanced. If you try to check the equivalent network, it has to the equivalent resistance should be the same at all the stages. But in this case, what will happen is for all these stages it will be equal. But when you come for the last bit, you'll not be getting that. Okay, it will not be equal, there will be some change. Okay, so that is because we don't have an resistor over here, okay, to balance it. Okay, so that is what we have done here in the circuit. So we have included resistance over here. So either you do the get the equivalent resistance from this side or this side, the value of equivalent resistance will be the same. Okay, that has to be the case when you're talking about a ladder network. Similarly, you can also create a ladder network using capacitance also. Okay, but it will be the other way, which you should be aware of. Okay, so I'll move into the next circuit. This is going to be the successive approximation register, and I have given the output at each and every stages so that it will be easier for you to check also. This is how we are going to get the value of successive approximation register. It has to count. Okay, generate the clock input to the input stage and then count the respective output, and you have to measure the hexadecimal number, so which we'll check as we move further. And this is going to be the sample and hold circuit. We can make use of this comparator, or you can make use of this sample and hold circuit. This is the comparator. Okay, so the input to the comparator will be coming from the sample and hold circuit, right? Either you can, anyway, it is going to be an analog data. Either you can use a sample and hold circuit, hold IC, which is LF398, or you can directly give an analog input voltage of any values. Mainly what we have to do is we have to calculate it for three levels of voltages. Okay, one is going to be the zero level, another one is going to be the mid level voltage, and the other one is going to be the full scale voltage level. So either you can go with this approach, or you can make use of a sample and hold IC. Okay, but for illustration purpose, what we have done is instead of using a sample and hold circuit, we are just making use of an voltage stage, voltage source, which is given over here directly to the input, or you can directly use a battery source in order to give the voltage at the input of comparator. Okay, So finally, when you put all of them together, you'll have the circuit like this. So first how we did this, let me explain how we did this. We created the sample and hold circuit. Okay. Sorry, we created the 2R ladder network. Okay, tested this one, and then we created a top level hierarchy for this, because the entire circuit will occupy too much of space. So what we did is we created a top level hierarchy for this. Okay, and the same case with the successful approximation register as well as but here you don't have any issues. It is all altogether available linearly. Okay, so R2R ladder DAC and the successive approximation register. First, we connected these two things, these two blocks, and checked for the output. Okay, we have to get a hexadecimal thing. Okay, and then we connected this comparator block with a voltage source, as I have told you. Okay, voltage source as a sample and hold input to the comparator. The output of this comparator is connected to this SAR logic, and then we used to run the simulation. This is how we have tested the blocks. Okay, so now let us move into the demonstration purpose. So by doing this, we get an idea of what to expect when we go for cadence tool and design a circuit using any type of technology library. Okay, that is the reason why we do all the designs on OrCAD first. uh, yeah, even in industry, this is the practice. First, they used to design the circuit on ARCAD, test it so that we can understand what to expect and what not to expect, and then go into design the complete the design on paper, get it on ARCAD, test the design, and then go into the IC design tools like Cadence or Mentor or Synopsys, whatever it is. Okay, as of now, all the tools are being used. And one more advantage with the arcade is it can be it is it is cross platform. It has access to almost all the third party softwares. Okay, you can combine the tools, or you can get the input from one tool and process it using OrCAD PSpice. Okay, or design it on OrCAD PSpice and get it to the EDA tools. Anything is possible, like MATLAB, answers, etc., everything. Okay, so that is another major advantage with the OrCAD PSpice. Now let us move into the demonstration purpose. We have already uh, we already have the designs open, because we don't have much time in order to do the schematic capture and then illustrate it. So we already have the illustrated circuit. Okay, so you can see the SAR logic, okay, top level design, and you can see the R2R ladder network, and here you can see the comparator. So for comparator, we are making use of LM339 IC from TI. To check out the properties of any type of ICs, what you can do is you can check the data sheet. Okay, so you know how to check out the data sheet, right? So you can look for the IC number, LM339 data sheet. If you search, okay, you can get the properties and and its applications. LM339 data sheet, you can search. Okay, so we have it over here. So you can check what is the type of device, what type of device it is. It is a comparator, and you can have a look at the supply voltage range, okay, and the applications of this particular circuit. So this is how you can select the uh, devices or components or ICs. Okay, and you can also have an idea of its pin allocation, which pin goes where, and the output, what to expect. Okay, maximum supply voltage, the differential input voltage that you can give, and what is the ESD ratings, and what would be the output for those particular input values. Okay, and this is given for different packaging levels. Okay, so this is how you have to check everything, and that's how it has been done even for this demonstration. Okay, so here you can see this is the SAR logic. Okay, we have used nearly 17 flip-flops. Okay, 9 at the top and 8 at the bottom. So why do we need this? Because we need to generate the preset. Okay, because when you talk about a flip-flop, the IC used is 7474. Okay, it is a D flip-flop, positive edge trigger D flip-flop. Okay, which has negative active low preset and active low clear. Okay, so for these things we have given the input digital stimuli, but what about the input and clock signals? We have to generate them, right? uh, it is okay for a single stage, but for the next stage, in order to generate the data, or because we are planning to give the pulses on as a clock signal. Okay, so for that we need to generate the input clock. So for that to be done, we have one more stage of D flip-flops. Okay, and let me simulate it and show you the output for the SAR based design. Okay, and I've plotted everything. Let me just run the simulation. Okay, so this is the input clock stimuli, okay, from the digital stimuli, and this is start conversion. Without a start conversion, it's not possible for the blocks to be displayed. That is why we have the start conversion signal, and then these are the clocks that are generated from the first stage, that is top level first stage of a D flip-flop, and out of that we get the output. Okay, this is how we get the output, and we have done it for we are running the simulation for 24 microsecond. Okay, if we run it for an extended period of time, then we can uh, see the exact result. So let me show you that. Let us run it for around 100 microseconds. Let us check it out. So we have the simulation profile over here. Actually, we have zoomed out. That is the reason we are not able to see it. We'll fit that to the screen so that we can check out the output. Okay. So this is how it looks like for 100 microsecond stop time of the simulation. Okay. And next we'll move into the R2R ladder network. So this is about the circuit. Okay, then what we do is we create a symbol. Uh, so uh, so to create a symbol, we should not have the voltage sources and all. So that is why we have neglected those things. We have removed those things over here. Just creating a copy of everything. Copy of the circuit. Okay, and then this is about the symbol. Sorry, this is the block. Okay, this is the symbol that we have created. We have to test this symbol, right, in order to check whether the behavior is similar or not. So for that, we create a test circuit, similar to whatever we have done in cadence in the morning. Okay, similar to that. So we are testing this SAR logic with these inputs. Okay, that's what have been done. And the same manner we have repeated for R2R ladder network also. This is the circuit. First, what we'll have to do is we'll have to check whether it counts all the 256 bits or not, because 2 to the power 32, what do we get? What is 2 to the power 32? Sorry, 2 to the power 8. It is 256, right? So it has to count right from 0 to 256 or 256 down to 0. Either way, either it has to count up or count down. That will be left to the designer. So here what we have done is we have made the R2R DAC to count right from maximum to the minimum, 256 down to 0. Okay, so let us run the simulation and check what it does. So it's running. You can see the progress over here at the bottom. So it's taking some time. Okay, so here it is. You can see it's counting. If you zoom in, you'll be able to see the steps. Okay, so I'll use this zoom in option. You can see the steps, and you can also check the maximum value of voltage. Okay, so this is how. If you place a cursor over here, also for placing a cursor, I'll use this toggle cursor option. And if you place it over here, you can measure the input and output voltages. So these spikes are because of the resistances. Okay, resistances and the capacitance that are getting generated inbuilt, as well as whatever is generated as a result of extraction. Okay, so that is why we get these spikes. Okay, so hope this is clear. Any doubts till now in R2R DAC and SAR, successive approximation register? Any doubts? If you have any doubts till now, you can let me know on chat, or you can also unmute yourselves and let me know your queries.
No, sir.
Okay, okay. Let's move forward now. Okay, so this is about SAR, R2R DAC and successive approximation register. Next, we'll move into the SAR block. Okay, so this is the SAR register. I'll close all the other blocks. So as I've told you already, we have created a top level hierarchy for all the blocks, because it will be highly difficult and difficult for us to uh, check or design the entire circuit once again. So it is always better to have a top level hierarchy for a bigger circuit, so that we can include them easily. So here what we have done is we have three levels of voltages. The supply, the operational amplifier is biased at 5 volt. Okay, so what we do is we take that as a maximum value, that is full scale value, 2.5 volt as mid-level value, and 0 volt as low scale value. Okay, so low scale, mid scale, and full scale. We are going to measure this for all the three values. So we'll start with full scale value. Okay, so what we can do is we can just run the simulation and check the output. And there are certain inputs which we had just for testing purpose. Okay, later on it is not required. Okay, once the testing is done, we can remove the sources. That is how we have done. Okay, so let me run the simulation. So you can see the input for this amplifier. Okay, so you can check V in and V out DAC. Okay, so there is the V in. You can see the input to the comparator. Okay, this is going to be the input to comparator. Okay, and this is going to be the output of DAC. Okay, so any doubts here? Any doubts, participants? Okay, if you don't have, then we'll move to the next level. Okay, which will be in uh, the cadence tool. Okay, so once we have an idea of what to expect, this is for a full scale value. Similarly, you can also do it for mid scale value, where I'll change the value of this voltage as 2.5 volt. Okay, if you change the value of this voltage as 2.5 volt, save the circuit and rerun the simulation, then we can have a look at the hexadecimal value. You can change, you should be able to see the changes over here. Okay, so mid scale in the sense, if it is 2.5 volt, then it has to be uh, uh, earlier it should have been FF. Okay, for the full scale value. So 1111 and 1111. Okay, same thing. If you're going for mid scale, then it has to be 7F 0 triple 1. Okay, and for 0 scale, then this has to be 0 0. Okay, that is how you have to figure out, okay, whether it is correct or not. Okay, so now we have repeated the same circuit on the cadence tool also, based on 180 nanometer technology node. Okay, this is based on ICs. Okay, so what all ICs we have made use of? For the comparator, we have made use of LM339. Okay, and if you take a look at the R2R ladder DAC for the switch, we have made use of ADG413B. Okay, analog to digital switch, and here we have made use of the ladder network, and the operational amplifier LM324 we have made use of. Okay, and buffer 7474, we have made use of two inverters to get a buffer, and digital stimuli, okay, to give the inputs at different frequencies. 8 different frequencies have been made use of. And if you look at the SAR, successive approximation register, we have made use of the D flip-flop, which is 7474. So these are idea blocks that are already available, designed and tested ICs. Okay, so by using this, we are going to, by taking this as a reference, we are designing a practical circuit. Okay, where the output can be anything. Okay, it might change, okay, based on the technology node values. Okay, so how to do that, and how to test whether it is similar or not, or not, cannot be exactly equal, but depending on the technology library, we have to check how it behaves. Okay, so we have the SAR ADC. So what we have done here is, we have a standard cell library for 180 nanometer. From there, we have taken this D flip-flop. The behavior is same as of IC 7474. Okay, so from where did we get this is in the library manager. We have GPDK 180 underscore SC. So here we can check out DFFSR X1. Okay, D flip-flop with set and reset, okay, of drive strength 1. That's what is the meaning of this. Okay, this is already available on KEDA's library. Okay, if you have a 180 nanometer technology node, then this will also be provided to you. Okay, you can check it out later. Okay, and we have given the inputs. Okay, uh, for data we have given the input as 0. For clock, we have given a
pulse source. So the technology node that we have made use of is 180 nanometer. So for that particular technology node, the supply voltage can be either 1.8 volt or 3.3 volt. So for proper biasing, we have taken the voltage value as 3.3 volt, and to neglect noise, it is always better to go for higher value of supply voltages, right? So that is the reason why we have taken the voltage value as 3.3 volt. Okay, circuit is the same as we have seen already on OrCAD PSpice. This is for a SAR logic. Okay, and we have created a test circuit for this. Okay, top level hierarchy. If you wanted to cross verify, then you can just peek down this hierarchy and open this. You can see it is the same circuit minus the supply voltage sources. Okay, so that we have included here already. If you wish to have a cross verification or cross check, you can do that. Let me run the simulation. Okay, so that we can have a check. So I'm plotting all these signals. Okay, I'm running a transient analysis for 100 microseconds. So let me run the simulation over here. It takes some time. Okay, okay, so this is how it looks like. If you wish to split it out, you can do that. So I'll go for graph and go for split all strips so that you can see the inputs and outputs separately. If you wish to check, these are all digital data, right? So if you wish to get it as a hexadecimal equivalent, then you can do that. So what you can do is you can go to measurements and then go for analog to digital, and here you can select the analog data that you wish to change. So for example, I need to change all these things. 8-bit data, right? So 7 down to 0 is what I select. Okay, and center value, let me give it as 0.5, and we are going to make a bus. Okay, if you we need a hexadecimal equivalent. Okay, so bus name as SAR. I name it as SAR out. Click on OK so that we'll get the data over here itself. Fine. So let me show that here. Any doubts, participants? I can see someone powered on the video. Please disable your video. Okay. So this is what we get. Now let us check the voltage values. Okay, we were talking about full scale, mid scale, and zero scale values, right? So if you consider here, it is a zero scale value. Okay, so if you wish to have it for a full scale value, and this is a SAR logic, we have to do that in the amplifier stage. Okay, not here, we cannot check that here. So as of now, I'll close this. Let us check that for the overall circuit. Okay, so next we have the R2R ladder network. Okay, so this is the standard cell that is already available, and here we have the ladder network. We can see it is balanced. Okay, this is a balanced R2R ladder network, and here we have an operational amplifier. If I peep down this hierarchy, you can see the operational amplifier, which we have characterized. You know what has to be done to design an operational amplifier of a desired gain or for a desired performance. Okay, we have to first characterize the NMOS transistor and then characterize the PMOS transistor, and then include, first we have to start with the common source amplifier, right? So we design a common source amplifier, connect them back to back, and here we have you made use of a single ended differential amplifier um, at the input stage, and the output stage is again a common source amplifier. So we have connected two common source amplifiers back to back, where NMOS transistor uh, NMOS pair is a differential stage. In case if the PMOS pair is the differential stage, then you can use the circuit in the other way. Okay, and we have the compensation capacitance and compensation resistance included in the circuit. Okay, to avoid in order to improve the stability of the amplifier. Okay, and this to our ladder network can be compared with the ideal block that is available here within the cadence also. So how did we do that? Let me show you that. Okay, uh, this is what we had designed in real time. This is a real time R2R DAC. Okay, so let us check its test bench circuit. This is the test bench circuit for an R2R ladder network. Okay, so what we did here, let me show you. First, I'll show you the results of this simulation. Okay, we have already saved the state, so let me open that stage. Okay, so you can note down the output over here. So for that, we'll split all the strips. For verification purpose, what we can do is, you can see these outputs, what they represent. Okay, so this is going to be the output. VDAC pulse in is going to be the output, because this is going to be the input to the comparator, right? So I'll take this to a new window, separate window. So I'll change its properties. Okay, so if you zoom in, you'll be able to check out the steps. Okay, you have to zoom in as much as possible. So it will not be a definite step. Okay, because here we have made use of MOSFETs, resistors, etc. So we cannot expect a definite step. But instead of, in order to get it, then you can make use of filters. Okay, you can make use of filters. You can use an RC tank circuit, low pass filter, high pass filter can be made use of, and the compensation circuit can be made even more stronger in order to reduce these spikes and all. Okay, so how to check whether it has come counted to 56 steps or not? Okay, for that, what you can do is, you can go for measurements. Okay, uh, analog to digital. Okay, select the signal. Okay, so center frequency, let me mention it as 0.5. I'll make a bus. Okay, and it has to be an unsigned decimal. Only then I'll be able to figure out whether it has counted or not. So this is going to be a digital to analog converter. So this is a DAC out. Okay, click on OK so that you can check it out. Sorry, I think I have made a mistake. Just a second.
Okay, let me check this out later. Okay, I think I have made a mistake. Let me check this out. Okay, so this is for an R2R a DAC, digital to analog converter. Okay, think I've done it the other way. Let me check this out. I think I've made a mistake over here. Let me check this out. Okay. So how did we compare is what I had been asking you about, right? So what we did is we have an ideal digital to analog converter and analog to digital converter. Okay, so we have created a test circuit with that. Okay, so where are those blocks available is in AHDL lib. In AHDL lib, you can see ADC 8-bit ideal, and similarly, we'll be having DAC 8-bit ideal also. Okay, so we brought these circuits together, okay, these blocks together, and created a test circuit. So where is that? Let me show you that. Okay, R2R, ladder attack, this one. Yes, we have it here. Okay, so what we did is this is the ideal um, analog to digital converter, and this is the digital to analog converter. Okay, and here we have the practical one. Okay, this is the ideal one. This is the ideal analog to digital converter. This is the ideal digital to analog converter. This is the practical digital to analog converter. Now let me show you the comparison results. Okay, so we have already saved a state. I'll just make use of these blocks. Okay, I'll just run the simulation since already we have selected the bits. Okay, we'll run it up to 6 milliseconds. So you can see. Since for ideal circuits, you'll be getting the maximum value, whatever is the maximum voltage value. But that is not that's not possible with a practical circuit, right? And you'll be having some discontinuities because of the CMOS transistors. That is the reason why you are not getting the entire value of voltage given at the input. At the same time, it also depends on the threshold value that we have mentioned here for the operational amplifier, because V logic high we have taken it as 4.5, and the reference voltage also we have taken it as 4.5 for ideal thing. Okay, that is the reason why it is going up to 4.5 volt, whereas for digital to analog converter we have taken it as 1.65 only, because that has to compare that has to be in sync with the practical value. Okay, that is why we have taken it in that manner. Okay, so let me take these three alone separately. Okay, this is for the ideal 8-bit ideal digital to analog converter. This is the output of your output of the ladder network. Okay, VR is the output of ladder network, and this is the input pulse. Okay, this is the output of your R2R ladder network. Input to the op amp, and this is the output of your operational amplifier. At both the stages, we are checking the outputs. Okay, and you can see almost everything are in sync with each other. Okay, all are on the same line. If you zoom in, you'll be able to figure out the differences. Let me show you that also. We are not saying that there won't be any differences. Definitely there will be some differences. Let me show you. If you zoom in over here, okay, so you can see the difference. Okay. So with this, you'll be able to measure DNL and INL that is associated with the um, mixed signal designs. Okay, so when both the steps are in sync with each other, then there is no DNL or INL. If it is, if the difference between the steps are less, okay, that is in the negative value, then you'll be having a DNL. If the waves occur beyond your ideal value, then it is an INL, okay, increased linear size. Okay, so this is how we compared with the ideal circuit and practical circuits that are available in Cadence itself. Okay, and then now let us go into the comparator circuit. So for comparator, we have an operational amplifier. Okay, so this is about the DAC, and finally this is your comparator circuit. Okay, so initially we tested it by characterizing, and then let me peep down the circuit. This is the circuit. Okay, we characterize the NMOS transistor, PMOS transistor, and for you to know how to characterize the PMOS and NMOS transistor, very soon we'll be having lab primer online training program only for the lab experiments, how to design an operational amplifier, how to design a differential amplifier based on a given specification. Okay, in order to check all those things, we have an online training program. You can register with us, okay, and take up that training program. Okay, so we characterize those transistors and we checked uh, for the behavior. Okay, and once we were satisfied with that only, we got it as an amplifier circuit. So here we have to check it for the functionality of a comparator, okay, and not an amplifier. So that part has been done. Let me illustrate that. Okay, so something is missing. Here we have to plot the output response. So we'll go for plotting the output. Then it's not getting plotted. Okay, let me close this and reopen. Okay, so here I'm going to plot the inputs. Okay, so this is about your input signal. So what are your input signals? B in P and B in M. Okay, it's going to be of opposite gain. So one has to be on the increasing side and the other one has to be on the decreasing side. We have to check the output. Okay, so output in the sense I need to plot this V out underscore 7P. So I'll just get that plot over here. So from design, I'll select this part alone and I'll run the simulation. Okay. Yes. So this is what I get. Okay, for the AC analysis, this is the curve that you'll get. Okay, and we'll have to check for the gain, and if it satisfies whatever is expected, then it is good to be used in the SAR based ADC circuit. Okay, so let us move forward with the design. We got each and every block one by one. Okay, so let me show you the testing stages also. We have all those circuits that we had used individually. Okay, so first one we'll start with your successive approximation register and the R2R DAC, those two tests. Okay, so you have the circuit over here, SAR ADC, SAR, and R2R DAC test. Okay, so this is the first stage. Okay, just the SAR based SAR logic and the R2R tag alone. Next, what we did is, along with these two blocks, we had included uh, we included the comparator. Okay, so along with these two blocks, we included the comparator. Let me show you that circuit also. Hmm. SAR ADC comparator test. Just a second. Sorry, I haven't uh, got those circuits. It should be there. Let me check. SAR logic to 4-bit. 8-bit test. Okay, we have it over here. Okay, I've kept it open already. So along with the R2R DAG, we have included the comparator also, right? And here we have the inputs. This is what I have. If not this, instead of using this, we already have the sample and hold circuit also, which is just MOSFET. Okay, we have the sample and hold circuit over here. Okay, either we can make use of this or directly give the analog input voltage as three different values. One is the full scale. Here the full scale value is a 3.3 volt. Since the technology node that we are using here is 180 nanometer, okay, 180 nanometer technology node, and for that the maximum value of VDD is 3.3 volt. Mid scale value is the bias voltage 1.65 volt, and zero scale is 0 volt. Okay, that is how we have to test it. Okay, so let me show it for the full scale value first. Okay, So I'll plot the output at each and every stage. Let me do that so that it will give you a clarity. Okay. So I'll go for launch ADEL and I'll run the simulation for transient analysis of 500 microseconds. Okay. So I'll run the simulation. So you have the values over here. Let me split the graph, split all strips. So we have the control bus. Okay, so I'll show you what all represents. Okay, clock is the input clock and start conversion. And these are all the input from the D flip-flop. Okay, input from the D flip-flop of SAR. Okay, that is what we have here. Okay, high and zero, everything if you want. Let me peep down this hierarchy and I can show you. Okay, new tab and here you can see. Okay, CF underscore init. That is what we have given here. CF underscore init, CF7 underscore clock. Okay, the output of the D flip-flop and it is going to be the clock for the next stage. Okay, which gives you the output of successive approximation register. Okay, and then control bus and the output from the successive approximation register. Okay, or the digital to analog converter. So if you wish to check the converted data, okay, so what you can do is measurements analog to digital and have to convert it right from QD7 to 0. Okay, so this is a full scale output. Okay, so center value I'll mention it as 0.5 and binary. I need the hexadecimal equivalent, right? So I'll go for hexadec, ADC, ADC out. So click on OK. So we get it here. If you zoom in, you'll get the actual value. Actually, we have two clock signals over here. So full scale, since it is full scale, we get it counted until the end. Okay, FF. Similarly, if we are measuring for mid scale, that is 1.65. Okay, so what I am going to do is, this is the input. Okay, you can see V in P. This is getting connected over here. The output of the digital to analog converter. Okay, output of R to R DAC is coming as the input to this comparator V DAC out. Okay, and here the control bus output is going to the buffer in order to remove the spikes, and the output of this buffer is given to the SAR logic. This is what happens. Okay, this output is what we are taking and checking it out. Okay, fine. Now we are going to do it for the mid-scale value. okay, which here in this case it is 1.65. So instead of 3 volt, if I mention the value as 1.65, okay, what happens? So I'll check and save this. Warnings, because we have some sources which we had used for testing. Okay, at the moment we are not connecting it. That is why we get those warnings. Okay, so I'll run the simulation once again. So you get the log file over here. It will take some time for the simulation to get executed because it is a bigger circuit, right? So that is the reason why it's taking some time. Okay, so please bear with us. Yes, so we have got the output. Now let us split the graphs. Okay. Yes. So now let us check the converted data and go for measurements analog to digital. So QD7 down to 0. Okay, 0.5. That is going to be the ADC out. Let me check it out. So if you zoom in, you can see this is C7. Okay, after reading it as C7, it's going for reset again. Okay, fine. Now let us check for zero scale value. Let us check what happens for a zero scale value. Okay, uh, so it is a cycle, and at all the cycles, we cannot assure that all the branches will be cleared because we have this different possibilities. That is the reason why we'll not be able to measure everything. Okay, so all the 16 bits we cannot get. Okay, let us see. This is for zero scale. In between, if you can take some random value also, even I'll show you that part also. Let this simulation get complete. Okay, so now we have got the output for this. Let us go for graph again. Split all strips. Okay, and we need to check the digital data, right? So I'll go for measurements, analog to digital. So let me check it out. QD7 down to 0. So let us check what is the digital data that we are getting. So you can see it's getting reset when it goes down to 0, 1. Okay, so it starts counting at respective digital data is what you'll be getting. Okay, at this, right? So similarly, if you are going for some random value like say around 2 volt, let us check what happens. Okay, so I am going for random value of 2 volt. Okay, let us see what it counts. And where it is getting reset. Okay, so this is for a random value. Okay, random value of 2 volt. Let us see for the digital equivalent. Okay, now it's getting reset at a value of EF. Okay, so it goes and counts 80, C0, E0, F0, E8, EC, EE, and EF. Okay, and then it gets reset again. Okay, so this is how it goes on. This is possible. It is possible to calculate it for any type of values, and you can also expand this to any number of bits. Okay, so I can see few chat messages. Okay, so participants are expecting for feedback link. No issues. Uh, so we have done this for mid value, zero value, low zero scale value, and the full scale value. In in return, we have also explained how to design a big module. Okay, this can also be submitted as a project. Okay, where you can show them the output at each and every stage of uh, the circuit design. Okay, because this is not an easy job of designing an analog to digital converter or a digital to analog converter. It takes a lot of time. Okay, we have nearly taken over 20 to 25 days to complete these blocks. Okay, and it's also very important that you check on the micro details. Okay, so for example, if you are designing a comparator, so what is the comparator made up of? It is made up of an operational amplifier. So what you'll have to check there, when the MOSFET is said to be in on state, when all the transistors are in saturation, right? So we'll have to check that also. If the transistors are not remaining in saturation, then obviously you're not going to get the required output as a functionality of a comparator. So how to do that? Okay, so let me show you. You have to just run a DC operating point analysis. I think we have run that over here. Let me close this. So you should also make sure based on the uh, circuit or devices that you have made use of in order to build a block. Okay, for example, if you have made use of MOSFET, then you should make sure that all the devices are in saturation. So I'm just running a DC operating point analysis alone. Okay, because I am going to check of whether my transistors are in saturation or not. So to check that, I'll just run a DC operating point analysis, and I'll go back over here. Okay, so I'll just peep down the hierarchy. I'll just open it in a new tab. And what you'll have to do is you go to view and then go back to annotations and go for setup. Okay, so here you can see the library. I have not chosen my transistors from analog glow. It is from GPDK 180, right? And from that, I have PMOS transistors and NMOS transistors. Okay, you can check on to you can select n number of components to be displayed because when you talk about DC operating point, you nearly have some 90 to 95 parameters. So out of that, you can select the most important parameters and display those things alone. Okay, so that can be done. That will give you a better idea as of how that can give you a better idea as of how it behaves. Okay, or how the circuit or whether you are getting the required output or not. Okay, so for that, what you can do is you can make a double click on component parameter and go for DC operating point. And here, this is one of the parameter, the drain current, right? That is required, okay, in order to check the drain current at this branch, and at this node. Okay, and then most importantly, you need the region. You need to check out the region. So for that, make a double click over here, and here you can select the region. Okay, you can see region over here, and then you can select VD sat. Okay, DC is drain saturation potential. Okay, and you can also go for transconductance. That is also another important parameter. So this is it. Okay, click on apply. You'll get all the things for the PMOS transistors, because I have selected only PMOS here. Similarly, if you want everything to be displayed for an NMOS transistor, repeat the same process. Just select NMOS transistor over here and select DC operating point, and here you can choose the parameter. Okay, I need the region, so I'll select the region. Okay, this is what normally we used to check. Okay, DC saturation potential, and then the transconductance. These are the parameters that we used to check normally when we are designing. Okay, click on apply. So for all the transistors, if you select apply settings to all, then it will be applied to all the transistors. So you can zoom in and check. You can see the region. So here in cadence, it is denoted as a region 0, 1, 2, and 3. 0 stands for cutoff, 1 for uh, uh, 1 for linear, 2 for saturation, and region 3 for pinch off. Okay, so these are the regions of operation. If it is in region 2, then obviously it is understood that the device is in saturation. So you can see PMOS transistors are in region 2, NMOS transistors are in region 2. Okay, and here also you can see all the devices are in saturation. Okay, that's it. Okay, so this is how we check everything. Okay, we check all the parameters and then we run the simulation. Okay, so it is always important to check the behavior of each and every block at each and every stage, so that you can make sure that the devices are giving you the right response and you can move further. Okay, so let us go for a quick recap of what all things we have discussed today. Let me go back to the presentation. Okay, Mm, just a second. Okay, sorry, I think my screen share is stopped. Let us go for a quick recap as of what all things we have discussed. So we started with the discussion of a brief introduction about n-tuple and cadence. What are the tools provided? Okay, let me list out the tools also at the end. Domains in which n-tuple is working on are channel partners. Okay, and these are the things about cadence. Okay, and then we had discussed about AMS design flow. Since we have an idea that it is a combination of both analog and digital blocks, we should be familiar with both the design flows, which begins with a full custom IC design flow, where we start with schematic entry, simulation, layout, physical verification, parasitic extraction, and GDS file generation. So everything starts with the input data from a market research analyst. Uh, and for schematic entry, we have a tool called which is a schematic editor. And for simulation, we have Spectre. For layout, we have Virtuoso Layout Editor. And for physical verification, we have Ashura or PVS. Ashura is for higher technology nodes, anything that is more than 45 nanometers. Anything that is above 45 nanometers, we go for Ashura. Anything that is less than 45 nanometers or 45 nanometers, we go for PVS. Okay, and then once the physical verification is done, we extract the parasitics, and to check its impact, we import the parasitics back into the schematic and rerun the simulation so that we get an idea on the impact of parasitic devices on the circuit. So how do you check? We just run a simulation transient analysis, and then we go for delay calculation. If we measure the propagation delay, then we'll get an idea. That is one of the methods. We have in other methods also, but most widely used is the simple way of calculating a propagation delay, which is easier when compared to other options. And then we had a brief idea of a semi-customized design flow, where we started with RTL design using any one of the HDL languages like Verilog or VHDL. Okay, and then we went into once the design is complete, we used to go for compilation, elaboration, and simulation. So we compile the design and to check the syntax and semantics, and then we elaborate it in order to map the logic that we have mentioned in map the logic that we had mentioned in our HDL languages along with the tool. So for that, we need some library mapping. That is what we do with the functional simulation. And then we synthesize the design. Okay, convert that HDL or RTL design into block level or module level design, so that we can get an idea of, okay, all these circuits are, all these blocks are made use of. This is the logic that is being used. This is the flip-flop that is being used. Okay, so to get an idea, we synthesize the design. Okay, once synthesis is done, we go for timing, area, and power analysis, which we shortly call it as TAP, timing, area, and power. Okay, so that will be different for different technology nodes, and even for each and every technology node, you have some processing corners like slow, fast, typical, slow, fast, fast, slow. You have certain processing corners. It will also be different for different processing corners. Okay, once these things are done, you go into DFT, mainly to check the reliability of the product or the circuit that you are designing. Once that is done, you go into the physical design part, which starts with floor planning. Then you go into power planning. Then you place your design in the form of standard cells, and then you realize the clock for the design in terms of sequential circuits. Whereas for combinational circuits, you don't have the clock signals, and then you go for routing, final complete routing of the design. Okay, and all these things are done with Innovus tool, and DRC, LBS, and QRC as usual is performed using PBS or Ashura, and finally generate the GDS file. Okay, and then we started with the topic of discussion, which is SAR ADC, successive approximation register based analog to digital converter. Okay, uh, it was based on the binary search algorithm, which was a technique used to solve mathematical puzzle, um, right, which dates back to 1500s. Okay, and this is the illustration we had given you in order to understand the successive approximation register, logic of successive approximation register. Okay, and then we go for the basic functional block diagram, which has a sample and hold circuit, comparator, successive approximation register, and a digital to analog converter. Instead of, we can use a sample and hold circuit that can be built using a MOSFET alone. Okay, or what we can do is, you can just give an analog voltage source. We can just variate between 3 or 4 different values of voltages, starting from 0 level, mid level, and full scale level. That is what we had done on Cadence. Okay, the output of the sample and hold circuit is given to comparator, and meanwhile it also gets the data from digital to analog converter. If the data from DAC, digital to analog converter, is larger than the input, then 0 is sent to the successive approximation register, or else if the input is greater than the output of digital to analog converter, then 1 is given as the output of comparator. Okay, that is taken as the input by successive approximation register, and based on that it generates a digital data. Okay, and translates that digital data to a DAT. Okay, so for building a successive approximation register, we had made use of D flip-flop. Okay, in terms of ORCAD PSpice, we made use of the IC number 7474, whereas in Cadence, we made use of set reset based D flip-flop with a drive strength 1. Whereas for a comparator, here in Cadence, we made use of an operational amplifier, which were in which the NMOS transistors and PMOS transistors, we characterized it for a particular value of gain. Okay, so here the gain was around 40 dB, I guess. I don't remember. Okay, and then for when it comes to ORCAD PSpice, we made use of LM324, which was an IC, operational amplifier IC, that was available readily in the library. And for sample and hold, we had LH398 in terms of ORCAD PSpice, whereas here we made use of a transistor. That's all. Okay, and for digital to analog converter, we made use of a ladder network. Okay, the output of ladder network was given as an input to an operational amplifier again. Okay, and the output of that operational amplifier is taken as the output of digital to analog converter. This is what we had discussed till now. Okay, and this is about how it works, uh, and the method in which we had designed the R2R digital to analog converter. Okay, how the equivalent circuit is how the circuit is minimized, and how we get the output voltage, value of output voltage, depending on where we give the input. Okay, if we give the input as the least significant bit, then it is going to be 1/16 of the input voltage, and if it is the LSB next to that, then it is going to be 1/8 of the input voltage, and similarly 1/4, one half of that input voltage. That is how we get the uh, equivalent resistance and output voltage, and this is a generalized expression for an for an R2R ladder network. Okay, this is how we designed using the ICs that were available in ORCAD. Okay, successive approximation register and sample and hold comparator. Okay, and the 8 bits RADC final block. Okay, before you connect the before you complete the overall connection, okay, it is always better to cross check at each and every stage, so that you can make sure that you don't lose the plot. Okay, you don't lose the plot, or you don't make it complex in order to identify where the mistakes happen. Okay, that is the reason why. So with this, we come to the end of this session, and let us move into the question and answers. Any queries, participants? You can unmute yourselves and let me know the queries, or you can also type it on the chat. Okay, we have some 20 to 25 minutes to discuss the topics of your interest, or whatever doubts you have, you can let me know. Anything related to cadence or whatever topics we had discussed, anything you can ask me. Any queries?
Dear participants, if you have any queries or doubts, you can ask now. Your mic also enabled. You can interact with our resource person.
Anything related to morning session, or this session, or related to the tools that we had discussed? TSMC, we don't have that, but Cadence supports TSMC technology node. Okay, you can reach out to any of the foundries, or you can let us know, so that we'll help you get in touch with the foundries and get the technology libraries. Yes, Cadence will support all the technology libraries. May I know from which college you are from, Sasikumar? Sasikumar sir, may I know from which college you are from? K. Ramakrishna College of Engineering. I think you had recently purchased Cadence, I guess. So definitely, yeah, Cadence will support all the um, TSMC libraries, UMC libraries. It will support. But you should be careful while extracting the files, because the technology node will have plenty of documents and plenty of tar files within each and every folder. So you have to extract everything. Okay, you have to extract all the files, go through the document one by one, because uh, we had supported recently for one of the colleges, and it took nearly 1 month in order to get everything up and running. Okay, so it will take some time for us to configure. Okay, yeah, thank you, Sasikumar. If you have any queries, you can let me know. Next, coming to Pallavi Tyagi, how can we calculate dynamic power dissipation? Okay, Pallavi, you are referring to the full custom IC design flow or semi-custom IC design flow? That's what I need a clarity on. Electron migration through Cadence Virtuoso layout. Okay, actually, you can send us a query on Cadence underscore support. Which college you are from, Pallavi? ABES Engineering College. Fine. Okay, so you can uh, send your queries to cadence underscore support. Okay, let me type the email ID. In case if you require any support, you can reach out to us. cadence_support@ntupl.com. Okay. Actually, I don't have an idea about electron migration. Okay. On Cadence Virtuoso layout, but you can let us know your queries so that we can work on it and get back to you. Okay. So full custom dynamic power dissipation, what you can do is, uh, so for example, if you consider the operational amplifier circuit itself, okay, so what you can do is you can figure out the drain current of the output stage. Okay, 7-pack op amp in the sense, the drain current of the output stage, which has the common source amplifier stage. Okay, and you know the formula to calculate it, right? So PD, dynamic power dissipation, is equal to VDD into the drain current. Okay, by using that formula, you can calculate it. Okay. Yes. Hope that answered your query. Yes, Pallavi. Yeah. Thank you. So next is from Kushbu Bansal. Can we write netlist with the cadence virtuoso? With the cadence virtuoso, you can generate the netlist file for the circuit, but you cannot write the netlist. You can write the netlist for you can write the netlist for this semi-customized design flow. There you can do it. Is that fine, Kushbu? Here we cannot write the, can we do simulation using notepad file? No, you cannot do the simulation using notepad. So can you let me know whether it is done, whether it is for full custom or semi-custom, Kushbu? Full custom. Okay, that's what I have I have demonstrated also. If you are doing it on a notepad file, you have to mention what type of HDL it is. Okay, that extension we used to give, right? For example, I created an inverter, okay, using Verilog program. Okay, so how do you mention the extension? Inverter.v. So you can import that into Virtuoso. I showed you how to import that also. If you want, I can do it and show you once again. So I can go to the command interpreter window, go to file, import, and here you can select the HDL. Okay, in case if you are writing it using Verilog, you can select that, or using VHDL, you can select that. Okay, and import it to the Virtuoso. Okay, hope that answered your query, Kushbu. Kushbu, did I answer your query? Sorry, I by accidentally I clicked on something else. So yes, you can include Spice file tool, that file too. That's what I said, right? OrCAD PSpice file can be used on Cadence, MATLAB, Mentor, Synopsys, everything. It is interoperable. That is one of the main advantages of OrCAD PSpice. Did I answer your query, Kushbu? Okay. Anything else? Or any other queries? Even you can see that option, Kushbu. I think I showed you right now. So file, import, you can see Spice. Okay. You can see the option, right? Yeah. Anything else, participants? Is my screen visible? Think now it should be visible. Yeah. Any other queries, participants?
Sir, there is a no more queries from participant side, sir. I think so.
Okay, sir. Okay. So just I'll take another 5 minutes. Okay. So in case if you have any queries, you can let us know on cadence_support@ntuple.com. Okay. And you can also mark me on the mailer. My email ID is naveen.shankar@ntuple.com. Okay. So for any training related queries, you can visit our website www.ntuple.com. Okay. In case if you have any requirements for training programs, short-term, long-term training programs, FTP, faculty development program or internship programs, we conduct training programs regularly, paid as well as free workshops. Keep visiting our website for free workshops and paid workshops. Okay. Let me take you through our website also and how to um, check those things. So if you search for Ntuple technologies, okay, you can see ntuple.com, right? So if you log into our website, this is how it looks like. And for training inquiries, what you can do is you can go into trainings, okay, and you can check out your learning domain, whether you are looking for VLSI, RF and antenna design programs, electronic circuit design and simulation, ANSYS, mechanical online internship, IoT or data science. Okay, so you can select our links. In case if you are looking for VLSI, you can select this. Okay, so you can see internship program currently. Custom IC design is about to start on February 23rd. Okay, we are starting a fresh batch on February 23rd, and the laboratory primer based on digital IC design, which is mainly concentrated on lab experiments on syllabus. Okay, syllabus listed out in various universities. Okay, we consolidate them and check out those experiments alone. Okay, so digital IC design lab primer is also starting by 22nd Feb 2021. Along with that, we have VLSI career builder programs on ASIC design and verification, as well as physical design and verification. You can check out those things. In order to have a look at contents, you can go for know more. Okay, and you can see what all topics are going to be covered. This is for CMOS standard cell circuit design, simulation and layout. Okay, you can go through the syllabus and the schedule. Okay, so this is how we have planned the programs, and this is for digital verification using Verilog. Okay, and these are the online ongoing program schedules. In case if you have missed out on something, no worries, the topics will be repeated. And if you have any specific requirements also, you can let us know on the email, so that we take some time in preparing those things, and we'll get back to you shortly. Okay, and these are the contents that we'll be discussing on digital lab primer sessions. Okay, and finally, for career builder programs, you can visit the same type. And electronic circuit design and simulation is also about to start. I think it is not yet updated. Maybe in second week of March, we'll start with this program. Okay. So That's all I have for you. In case if you have any queries, you can let me know. Any other queries, participants? If you have any other queries, you can let me know, participants. Yeah.
Sir, I think there is no more queries, sir.
Okay, sir. And I think we can
Let me widen up the session, sir.
yeah.
Okay, sir. When educating the minds of our youth, we must not forget to educate their heart. In this way, I would like to thank our today's resource person, Mr. Naveen Shankar, Field Application Engineer, Entable Technologies, Bangalore, for providing a wonderful session on the topic of design of SAR-based data converter using a Cadence EDA tool. On behalf of organizing team and Kongunadu College of Engineering and Technology, we once again thank you so much, sir.
Hello.
Sir?
Should I stop sharing, sir?
Yes, sir.
Yeah.
You can.
So thank you all. Thanks for your patience. And in case if you have any queries, you can let me know now. Or you can reach us at cadence_support@ntapl.com. So please let me know your feedback on these two sessions, overall feedback. Negative feedbacks are most welcome. Rather than giving it on feedback link, I think I may not have any access to that. So please unmute yourselves and let me know your feedback, or you can type it on the chat box also. Feedback participants, I'll not hold you back for more than 3 or 4 minutes. Thank you, Pallavi. Thanks. Thank you very much for your feedback. Anybody else? Practical session helps us a lot. Okay. So yes, if you are having any practical sessions now, okay, or if you are looking for any practical sessions, you can reach out to us. We even provide tool access to all the participants who are attending our training programs, like the internship programs and short-term training programs. You can reach out to us. We provide tool access on a paid basis for a duration of 2 hours. Okay, you can let us know in case if you need access to the tools. Okay, yeah. Anybody else? Please give me your feedback. We have it open for another 2 minutes. Thank you, Kokila ma'am. Thanks for your feedback.
Thank you all. Hope you'd have enjoyed a lot. Even I enjoyed. Uh, Thank you once again. Thanks for your patience. Looking forward to have a discussion with all of you in some other training programs. Thank you all. Thanks.
Thank you, sir.
Thank you, sir. Thank you very much.
Thank you, sir.